All right, so now it is time for me to really explain why has it been so important that I keep talking about tangent lines or equations of tangent lines. Okay, so in that way, here I would like to introduce the concept of rates of change. Because now it is time for anyone who has been following with me and who has been studying with me to know why the equation of tangent lines are so important. And it's not only just a problem we do for fun. It's having such a diverse amount of applications out there. So, and all that stays behind that concept of being rate of change. Okay, and so I am going to again quickly erase the title of our discussion here, and let's get into really in-depth understanding of what a rate of change is all about. All right, so at this point, let me bring up a graph. And so in my graph, I just simply say, and we don't have to worry about what function that is. Let's just say generally we have a graph. And this graph here, y is a function of x. Okay, and so the graph here, the vertical axis and the horizontal axis, we put the output values or the dependence variable on the vertical axis and the independence variable on the horizontal axis. And so in how I'm seeing, then, and a graph like this, like I said, let's not be too worried about what function that is. Hey, is that a cubic? Is that a square function? That's not the point to be worried of right now. What I see is a graph. When we sketch the graph of something like this, there could be, and the graph could be something like this. Okay, so let's say our function f of x has a graph like this. So this is the graph for f of x. And so your algebra instructor should have mentioned this, but in case he or she mentioned and it faded away in you, here I remind you again, the whole point of viewing and understanding a graph is that anytime looking at a graph, you must be looking at the graph you must investigate a graph from the left to the right. Can we set it clear on that? Can we all set it clear on that? Anytime looking at a graph and viewing a graph, we must be viewing it from the left to the right. Okay? And so now, and another brief reminder about the whole point of function is that we are trying to study, because a function is a relationship of two separate quantities. The x variable is one quantity that we call the independent variable, and the y quantity is, here in the concept of a function, is a dependent quantity, because so now here's what you can see, and combined together with what I was explaining earlier, that when you're viewing the graph, we're viewing from the left to the right, then as we are changing values anywhere from the left to the right, as we are viewing the values of x on the left, from the left to the right, then the y values represented by the vertical coordinates here, they are rising, and they are falling, and they are rising, and they are falling. Okay? Because the truth of life is, anything in life is changing. Any quantity, any amount of is changing. And so think about so the reason I was asking to look from the left to the right is that simply because as we always let the variable x changing in a way that it's always, we always going to change from 1x, lower value of x, to a higher value of x. Let's investigate how the y value, how the function output value changes. So for example, now if I start out here looking at a value being x equals a right here. So at a, then I have a function value being being y, but namely this is f of a, the function output at x equals a. But then when we change to a different, and again, as I said, let's stay in the convention that we're looking at the change in x value from the left to the right. And so as we change to a different value on the x-axis, change to a new value, then of course our y value changes to a different value. Now I'm not going to say right now about being higher or being lower. That's not the point, but we have another value for y right here. So when our x value change to x equals b right here, then our y value change to, so here f of b right here. Okay, and that's the whole reason why a lot of times when we're looking at graph, there are ups and down, crazy all over our graph right here. Okay, and so where do we see these in our daily lives applications? Where do we see functions in our daily lives applications? And so back in the days, any of you study about algebra, it's probably pretty boring, deadly boring that we have to look into these applications, but they really are from your daily lives application. So think about, let me quickly make some cleaning up of my picture over here and to hopefully try to retain most of it. So far what I have said is that a lot of time we have two quantities, and one quantity is being dependent on the other one, and that's the whole idea about function. So briefly, that's what I said. And another thing I have to point out, every quantity in this life that we're living in changes, okay? And so that's the whole reason why as we change our values of the independent variable, that will consequently change our values on the dependent variable. And that's why we're calling them the independent and the dependent variable. Okay, but now I'm about to bring up some brief little examples of where you see these quantities in your life that we have to represent them with the functional concept, with the functional understanding here, with the graphical understanding. Well, the most basic concept, do we walk? Okay, do we make motion? Okay, so yes, I can walk in assuming I'm walking in a straight path, I walk back and forth right here. So if I reference to where I started out here as a 0 point, then as I walk, maybe a few steps, maybe a few feet, then I have made some distance. And now once I have made some distance, I'm going to walk back to where I was, maybe, but not as much. So I walk a few. So that's the idea right here. So maybe I need a different graph. So maybe at the instance of a starting point. So in that way, think about it. The x variable could be regarded as the time variable. So x could be time, okay? And at some time instance being whatever time of the day you're starting out, okay? And then at some original point of yours, you're at how about 0 meters? So y here is the meters, for example. Then at some point when you change. See, and notice when I was walking briefly to demonstrate the idea of how I made motion, then time is always gone by. See, the moment I stand now and the moment I get there was two different time instances. And so the same way like that. So when I started out at A, originally I make 0 distance, but when I get to B right here, then I gain some distance. Now, don't worry about the shape of my graph, but the point I want anyone to see here is that as time changes from some initial point to some final point, then we have gained some distance. And that distance is the vertical y value, is our output value. That's the y value right here being. So when I'm at the time instance, some b seconds later, okay? I mean, at some time interval later, then my position is the function value at that time instance, okay? And so that's the closest application that we can see in any of our daily life. And think about it. When I was walking toward and I was walking back a little bit, think about. So we gained distance as I was walking away, but then when I was walking back, the graph could have gone like this. So we gain some graph, but then we're gonna have to drop back down. So when I stopped, but I didn't walk all the way back to the beginning position. So I was somewhere out there. somewhere down there. So at some time later, some other later time instance, maybe x equals c right there. My position, my distance away from where I started, drop down. So that's why there was a rise and drop and rise and drops all over. Okay, and so that's the closest example right in our daily life. Everybody is making some motion. Everybody is moving. Okay, no one staying stationary the whole time, the whole day, throughout the entire time of your life. And now, even if anyone is sitting stationary for a really long time, what's the graph going to look like? What's the function going to look like? If I just stand here 5 seconds, 10 seconds, 20 seconds, all my whole life, makes no distance, then the graph is going to look like this. As time goes on, so here's the time axis, because right now I'm referencing to the time as the independent variable as the time variable. Then so the x here, as we always time always goes on. Okay, but if you stay right at one spot, then you gain no more distance. You gain no distance. No matter how far you go in time, if you stay stationary, then your graph is going to look like that. Okay, so that example lives right there in. I'm just quickly trying to point out how functions play an essential role in your daily life like that. Okay. If you feel like, and if anyone watching this video feeling like you don't have to worry about walking, I mean, who cares about walking? Who cares about making motion? Then well, we can see other applications. This is probably a good application, a good example for the social scientists, but who study about how our population is growing. We are human beings. We reproduce. Okay, and of course, there's a truth that nobody can escape from. Our human population is growing. Okay, so let's say, and we don't have to go all the way back to the origins of human being, where human came from. We don't have to go all the way there. Just start out with some years, okay? At some year, and we call that time zero, some starting point. And then, again, in years, let's say 2,000 years later, okay? And at start, we have about a few hundred. I'm making up a scenario right here. And then, so the vertical axis here can represent our population that I call the letter P. So instead of using x and y's all over every single time, we can switch to, time is t equals the amount of years, and then p of t is p stands for the population amount, how big our population is, how many human beings in the population, okay? And so, say in 2,000 years, and if anyone really have records, and looking back, then we have maybe our population has grown like this. Okay, so what is that indicating? As time has gone by for about 2,000 years since that, whatever day we call that the beginning days, right? Then our population has reached from this low to that high. Okay, and so it's it's entirely perfect to say that the population is a function of the independent variable time. The more time, as time goes on, at different time instants, we have different population amount, population size to be precise, okay? And if you're still not convinced about this example, because maybe some viewers don't have to pay attention about how big the population is, then what about when you are doing business? This is important. Everybody is doing business to make a living. Whatever business you're doing, it's a business because you're earning income. And so let's say income is your own, I can use a letter P again for profit, your own income that you can use that money to enjoy your life. Okay, so we can think about the time that you start your business, to start making a living, and to the day that at some time later that you look back, and then to find out whether you have done well. Then maybe and some people, they start their business from scratch. That means zero profits at start. And then over the years, they've gone up and gone down and gone up and gone down. Okay? And so at some T years later, at something like that, and they looking back and they were like, oh boy, there has been a lot of ups and downs in my business. So, but admittedly, in the end, I still gained some. I have still made some positive change, because at this point now, compared to when I started, say I'm pretending I was that person opening this business. So the profit here has been going up and down, a lot of up and downs here, but in the end, well, at this point, referencing back to the very beginning days of my business, then at some 8 years later, then I can see that I made some progress compared to the beginning days where there was zero profit. Okay, so let's not waste time to keep searching back at these examples. Trust me, you after this video, you look right there, you look a little more closely into your daily life right there. Everywhere there's a quantity, because profit is also the quantity, and time is always a quantity. Okay, and so as the independent variable change in your applications, the dependent quantity will also change. Okay, and so now I just made you, hopefully made you understand that there are always that phenomena, that natural phenomena about, you know, one quantity changes depending on the other quantity. Okay, and so now in that way, so back to the walking little demonstration that I was doing earlier. And we've learned about that concept speed since what, second grade, third grade, but let's now really give that an in-depth understanding, okay? Because it refers to how fast we're going. Then we can think of the situation as the following graph right here. So for now, let's keep it a simple graph. And let's assume that the path from home to the bus stop is a linear path. I would like to reserve all of the more complicated motion problem for the physics instructors to explain these for you. But here, let's just assume that we only walk on a straight path, a straight linear path from your home to the bus stop right here. Then home is zero distance, because that's where you live. You didn't make any distance. But by the time you get to the bus stop, you made some y distance. You made some y distance, and that y distance is some function value. And so when you start leaving your house, and by the time you get to the bus, it's x equals, and again, let's say x is a time parameter. And so when x equals some a seconds later, right, and from home and to x equals some a seconds later, then you're going to reach to some distance. Okay, and so your graph is going like that. So this is f of a. Okay, and so that's just to indicate we have a height here indicating, but that's on this graph right here, the vertical height is to represent how much distance you have made away from home in that amount of time, And so now when we've learned about walking since we were little, and we talked about speed and all that since what, second grade, as I said earlier, and now it's time and now it's time to look a little more in depth into that. But see, what exactly is speed? Because we want to find out, because from when you start to when we get to the bus stop, right, there has been a change. There has been a change in time. So the final time here, what I see here on my graph, the final time is a, but my initial time is 0. And then and think about how much change in distance I have made right here. How much change in distance? By the time I was at home, then I'm at f of 0. And by the time that I get to the bus stop, I was at some distance, f of b. And so this total vertical coordinates change right here on my graph is to indicate how much distance I have made. And a minus 0 is how much change in my time on the x-axis. Or another way of seeing that is the length of the interval of time, the interval of whatever the independent variable is. And so this thing I'm bringing up here, and let's set it up as a ratio, then what we see here, it's a ratio as I just said that. And so in that way, this is exactly the speed concept that we're seeing, because this is how much distance per that much time. So now further in a more advanced mathematical understanding, then this is the change, right? The change in position in your distance. Okay, the change in your distance that you've made over the change in time. Okay, it's the change in time. And that is that speed concept that we've been looking at since second grade, since third grade. But now mathematically, it's just how much change in the vertical coordinate over how much change in the horizontal coordinates. And so this change here in the way how I'm seeing is, so as I said, it's a rate right here. And let me now put on another graph right here. So this change compared to something like this, still somebody else is walking, or maybe a different day you're walking to the bus stop, and on that day maybe you're starting out leaving the house late, so you really have to go fast. So by the time that you get to the bus stop, it takes you less time. Let's say you're leaving home at 0, but in only a few seconds later or a few minutes later, a much smaller amount of time right here. And when you get the same distance, I purposely draw two graphs with the same vertical y coordinates right here, but in less amount. But now in the second graph, we spend less amount of time, so the change in time here is less. Okay, so for kids, for children, they're seeing this as we walk faster on that day that we are late for the bus. Okay, but the concept here again is there's a change in, see, this is the function, your distance at the final time value. See, that's vertical coordinates. And this is your function initial value right here at, so I'm looking at, so investigating that total change in distance, we're looking at f of a minus f of 0 again. Okay, the final time, another way of saying that, the final time, the time when you finally reach to your destinations, and then subtracting the time of when you started out leaving your home right there. But then the amount of time we spent doing that in this problem is only, well, maybe I shouldn't use the a in here. Maybe I should use some value b to indicate that it's a different value with a. It's a different graph. Okay, and assuming that b is a lower value, less value compared to a in the earlier graph. And so now if we're looking at the two graphs here, then this is a speed. But look at how quickly rise up our line right here, our graph right here, how quickly going up our graph right here, because it makes sense that way, in the way how little amount of time that we have to reach that much goal, the same amount of goal walking from home to the bus, right? And we have to crank out, we have to run really fast just to get, so running really fast means in a little amount of time we can still reach that much. And so now setting up as a rate, we can see graphically that this graph rise a lot more rapidly compared to the other graph. This is maybe like you're walking to the bus stop, the bus station's nearby your home in your usual pace. Okay, but now maybe in some of your days that you are late, then you're gonna have to finish getting there by a much less amount of time. Okay, but in the end, again, what I see here, the way how I see the ratio that I just now set up is again in the numerator. That difference there is the change in distance. And we're setting that up as a ratio, as a fraction over the change in time. Okay, it's a change in time. And so ratio Okay, change in distance, change over change in time. Ratio again, change in distance over change in time right here. Okay, two graphs I brought up and relating with the speed problem. And the same can happen with business problem about, you know, your profits is rising up and falling down and rising up and falling down and all that. Okay, but generally what I would like to point out now is that these change in distance over change in time is more like a specific for the speeding problem. But the idea now is that, again, we use the vertical coordinates as a y variable in this graph, and the same with the other graph. The vertical coordinate is to represent the y variable. And so here change in distance is because we applied in our applied situation, the y variable is the distance and the x variable is for the time. But in other application it's different thing. But generally what we recognize now is that, allow me to erase the board a little bit, but the change in throughout the two graphs I've been doing, then mainly the idea now is that it's the change, shouldn't use that symbol too early. This is the change in y, okay, over the change in x, okay. And so now this is what rate of change is all about. This is what rate, because as I said earlier, it's ratio, okay. So it's a rate, it's indicating how fast the vertical coordinates is changing over the horizontal coordinates as a ratio. So that's why we refer to this as rate of change, okay. And your algebra instructor back then should have mentioned this, okay. And from that point on, the change, it's a difference. Change is a difference. We have to do a subtraction problem to find out how much change. And so in that way, you must have seen this famous symbol, the delta y is indicating the change in y over the change in x, delta y over delta x. So that's generally what the rate of change is all about, okay. And so let's not rush into doing any example, and because you actually, I believe you must have done a lot of examples about these kind of problems back in your algebra. So let me keep talking a little more about that so you will understand. So let's look at the graph where I had here again. Then assuming right now that I'm just simply connecting here as a line right there, as a straight line, a straight segment on my graph right here, then what do we recognize? And I will get a little further into that. Thus, change in y over change in x right here as a ratio, as a rate of change here is indeed, this is the slope, right? What we right now, it's just something I trigger your understanding right here. It's this little ratio right here. If now graphically looking at that little segment right here, then it's the slope of the segment, okay? Okay, so keep that in mind. So now we're gonna, once we've had this, once we have seen this kind of problem lives right in our making motion problem right here, then let's really generalize the idea. And from that idea, we're gonna extend that further to understand more in a broader understanding. So now let me erase this. So here's let me now bring up another general graph again. Okay, so let y be some function, and your function there, once again now the output value for y could represent a lot of things like I already brought up. It could be the profits over time, okay, or it could be, you know, the distance over time, okay, or it could be population growth size over time, okay. And it looks like Mr. Dung used a lot of time here, but you know, as you get more advanced and apply your concept here into different situations, time is not the only variable that caused your function output to change. But now let's say back to this problem, the variable x is on the horizontal axis, the variable y is on the vertical axis, and we have some ups and we have some down and some ups again. And so So now, generally speaking, applying what we have learned about the speeding problem, about the motion problem, and so let's say when we're on the x-axis, when we're starting out at some time a right here, some time instant a, then at that instant, let's call that it's the initial time, okay, or the initial x value, because that's when we start. And then again, just like how I said, we're always looking on the horizontal axis, we're always looking from the left to the right. And so along that way, our function rises or falls, or rises depending on how the function x variables, the independent variables, moving, changing from the left to the right. So let's say when you hit to some later time x equals b, this later time instance to the right hand side of a, let's now call that it's some final time, or I keep using time because maybe part of it I study a lot of physics too, but so final x values. And so here, when you are looking for that point on the graph right here, when x equals a, then yes, the height here, this height is f of a. And then when we have reached to x equals b right here, then on the graph we are at another point right here, and that point is having height being understood as f of b. And so now more formal term again. This is y, but that's initial having a little bit of hard time writing this on my narrow board right here, but this is initial y value versus this one here is the final y value. Okay, and so now again, from this point to the other point, there's a change. How much change in x? Because we can always subtract out the final x value with the initial x value to find out how far the change from x equals a to x equals b. And so now generally, once again, the rate of change on any function is final b value. I'm not saying that final y value has to be higher. It could be, see, in a case like this, when a is here, and if your b is here, then your graph is getting to a lower value. But the point is final y value, or final function value at b, minus initial function value when x equals a right here, divided by b minus a. So here it took me a lot to kind of reveal this, but I really want you to nail down that concept right here. But this is called, it's a ratio, okay? So this famous thing right here now is called the rate of change. That there is called the rate of change, okay? It looks a little awkward that I write the name of this thing kind of way too far below. So let me erase a part of my board here and saying now all that ratio here is the rate of change. Okay, it's a ratio, it's a fraction of how much change in y in the vertical coordinates over change in the horizontal coordinates right here. And it's the difference in y value over the difference in x value. There are just so many ways of interpreting it. Okay, and so now let me bring up an actual computer generated graph right here to have a closer look at rate of change right here for us to realize. So now here we go on our graph that I have already prepared. We don't need to worry about what function this is. Okay, we really don't have to worry about what function that is. But right now, how I see it is that we're going to have a starting point. Okay, so right here at my starting point, see, a on the x-axis, my x-axis is here, my y-axis is here. So a on the x-axis there gives me some y value being f of a, and that's how I label it. This point on the graph, So this graph right here is showing some graph of some function f of x right here. So f of a is how high this is. And then when we change the x value to another value, so let's say now I'm going to put on, see, so from a on the x-axis, now we change from a to b, then notice how the function value change. I'm not saying it always have to be higher. Now in this graph in particular, it is higher. So f of a, the height for f of a is a little lower, but the height for f of b is, in this graph it seems to be higher. But in the end, well, that distance between a and b on the x-axis here is is that distance from here to here. And so it's that distance, okay? And so this distance that I'm drawing in dotted line right here. And so in that way, see, now it's clearly see that the change, the delta y that I was talking about is right here. You can see that I'm describing that right there on my graphic there. And this is my delta x, okay? And so just like that, the rate of change, that's why we got the delta y over the delta x, f of b minus f of a, to give you this distance, how much precise change, right? And then over how much change on in the x-axis interval. And then so now in this clean picture of the graph right here, allow me to, so let me zoom it in a little further so that we can have a better look at that. But now let me really connect these 2 points, because this is initial point and this is final point right here. Let me connect those 2 points by just connecting like that, okay? And so now, does that picture now recall some concept that we've learned earlier in the quarter right there? Well, connecting the line like that, like in what my picture is showing, then connecting a line like that, or here in this graph right here, if you connect final point with initial point, then you will get a line. You see, it's just the way, Euclidean geometry says you connect any 2 points, you get a straight line. So that's what it is. You got a straight line, okay? But now with that straight line, or the straight line you see on the graph I'm showing right now, that straight line there, isn't it obvious that this rate of change is the slope of that straight line you see? This rate of change is the slope of that straight line right there, okay? Because it's indicating how much rise. In this case, it's rising, right? In other problem, maybe if initial is here and final is here, then it's a fall, okay? But in the end, it's a rate of change. The rate of change is the slope of the line, but this line is going through, or on my graph right here, this line is going through the 2 points from A to B right here. Kind of just straight through, passing through the 2 points on my graph. The initial point is here, and the final point is there, okay? And so what's that truth I'm trying to point out right there? So this rate of change, and now I can just save that space right there. But on my other board, okay, so on the other board, so the rate of change, right? What I was trying to say earlier is that it's the slope of the line, okay, passing through the 2 points. Those 2 points are A, comma, f of A. And the other point is B, the later point, and f of B. I'm not saying f of B have to necessarily be lower or higher, but these are 2 pair of points. Initial point is here on the left, and final point is here, B, comma, f of B on the right. And so this line right here, the slope of this line passing through, obviously it's passing through 2 points. And so passing through 2 points, so it means what? It means this line that we're looking at here, the line we're looking at here is indeed, it's only a secant line. It's only a secant line. It's the secant line of the graph because it's passing through the graph as 2 points, and this point on the left right here is the beginning point on our x interval, and then this is our final point on the x interval right there. And so we came to that understanding that the rate of change is the slope of some line. But that's just what we learned back at the days we were still studying about algebra. It's just that way. And after those classes, those lectures, we've learned about algebra, about slope, about the rate of change back in algebra. Then we walked out of class, be happy, and took it like that since that day on. But now, as we grew more mature in mathematics, let's reinvestigate the whole situation over. Because here's the thing. What matters now is the rate of change we're studying there, that, or another way of saying is the rate of change we have already studied in algebra, the accurate rate of change. Okay? That's what matters right now. Because here's the thing. So let me really bring the camera to on my screen right here and do a couple of refinements right here. But so let's say your starting point on the graph is here, and you have a final point, and it made some distance on the x-axis. Okay, but then, and we call this slope here, this ratio of y over x, changing y over changing x, as the slope of the line right here. What I called it a secant line earlier, but it's not that important. But the idea is that, is this always the accurate rate? Because here's the thing. And as a matter of fact, look at how bent this curve of our graph is. And so if I was drawing a smaller interval, you see, if we have a smaller interval over here, for example, and I hope my demonstration is clear enough, but the idea now is that if we had a small, or basically we have a different interval, then the slope is different in each of the little intervals here. So I was starting at about somewhere about here, and our b value was about out there. But so what I'm trying to say now is that if we break that into little intervals, then we're going to encounter a different little slope here, and there. So now and that's the part that I want to point out, as we grew more mature, we've learned that this kind of the rate of change is not the accurate one. Okay? It's not the accurate one, because now on the graph, like the one I drew on my computer screen there, see, A is here, and so yes, that point right here is f of A, or A comma f of A, and then B is here. This is B comma f of B, and this changed. The point now is I'm trying to make here is that this rate of change here has skipped out a lot of other little rate of change, because what about in these smaller little intervals from A to, how about from A to C here? The rate of change is about this little slope right there. It's not as steep. See, it's not as steep as something like this. Okay, this little slope in my little interval is only here. And then from here, from C to, let's say I'm going to call this smaller value D right there. So from C to D, a smaller interval in there. There is this slope is different. This slope is different with that slope. Okay? And then from here to here, all of a sudden we have a really steep slope right here. So there has been a lot of changes in speed as well. There has been a lot of changes in speed. And I only broke down my total interval from A to B on the x-axis here to only 3 sub-intervals. And anyone viewing my video can already see that there has been a lot of speed that in the middle intervals of time, or in the middle little intervals that we already skipped out, we only get the overall one. And so that gives you a sense about how inaccurate this is. It's not accurate. It's just not the best kind of rate of change we're looking for. But sadly, back at algebra, that's all we do. And so now think about the idea, even if we're putting ourselves in little smaller sub-intervals like this, each one of these may be better accuracy than the overall guy like this, but in the end, it still skipped out a lot of the little changes in the little smaller sub-intervals. So the story will never end that way, because the idea now is that a rate of change throughout an entire interval, from a rate of change throughout a definite interval like this, is not accurate, but that's about the best we could do back in algebra. So now if we're looking back at that kind of thing, yes, the rate of change that we simply obtain by just, again, I recall that formula I just now wrote and had to erase, simply changing y value over change in x value. That kind of rate of change, the way we're doing here back then, the way we did that back then was definitely we had to do that over a finite or a definite interval like this. Okay? And so, and yes, that's how it all came out to have all that delta y over delta x concept. But now, sadly, this rate of change here, yes, it was a rate of change. It was the rate of change. But then this rate of change here, sadly, can only be referred to as the average rate of change, just indicating that we kind of average out all the little, so in an interval like that, we have to average out all the little rate of change in the smaller intervals to get some like that. And that's why we call it, it's the average rate of change. It skipped out a lot of details. But that's about the best we can do. That's about the best we could do back at the time of algebra. Okay? But see, as applications became more complicated, and our human minds became more mature. Okay, so we studied about rate of change, and we are not convinced about this kind of rate of change that back in the algebra days we were studying about. Simply a rise over run or a fall over run is not telling the whole truthful story. And the best place to bring out here is think about those people who are doing business. Okay, their business profits, really, it's rising up and down and rising up and down in every instance of their career. Some interval is rise, some intervals is fall, but if we brutally take an interval like that, then it seems like there hasn't been a large change. But if we look into some smaller one, then we found out that, hey, there was some big change. And then there were also some big drops. Business people have a lot of up and downs in their career like that. And so now what about us? If we don't do business, what do we see? When we're walking, can anyone viewing this video guarantee with me that you can always walk at the same pace? No. Like a bus stop problem I was pointing out earlier. Maybe even on some day when you are already walking on the road and you decide, I'm late, walk faster. Okay, so the idea is like this. Maybe you were walking at steady pace, but then at some point you decided you have to hurry up. And so steady pace gives you kind of like a straight, linearly going up like this. And then after that, rising up, you have, see, in about the same amount of time, but you gain more distance. See? This is more distance gains compared to that same amount of time, but you have less distance gain right there. Okay, and so that's the idea so what I'm trying to point out now is that there is this kind of speed, there's this kind of rates that there's this kind of rate that we want to know. It's still rate of change, technically it's still changing y over changing x. Okay, let me draw a graph like that again. There's this kind of rate that I want to call, it's a rate of change again. Okay, but start thinking into this. It is possible to think about there is a kind of rate where it only exists in one instance. The kind of rates that only happen in one instance. Think about when the interval gets so small. Well, the interval like this, then the line is kind of connect through as a secant. But now when the interval becomes so small and eventually it hits to only 1 point and we so-call one instance. Ladies and gentlemen, in your calculus study now, this is probably the first time you hear this is called the the instantaneous rate of change, the kind of rate that happens only at that instance, and in the next instance, how far away to the next instance, nobody knows, and it's not the point, but at every instant it's a different rate. And so that's why I kind of revealed the truth a little too early, but that's where the slope of tangent line is for. Because, so, see, if we had an interval, if this is your some initial point, if we had an interval, a finite interval like that, and drew a line through these 2 points, so that's just average rate of change inside of this interval from A to B. But now if anyone desires to find out, hey, what happened to the speed? What is that speed, particularly only at that point, where now I introduce that term, the instantaneous rate of change, the rate of change that only took place right at that instant. And no matter how close the next instant is, it's going to be a different rate of change. Okay, and that's why that's still a slope, but the kind of slope there is the slope for this tangent line. Okay, because so now back in the days that I was explaining about the limit definitions to find the limit definition to find derivative right here, to find slope of tangent line, and I was pointing out that as we were squeezing in the interval to make the interval smaller and smaller and smaller. And you observe through my graphical representations that this secant line slope kind of rotate, the secant line rotate right around that initial point A right here to eventually become the tangent line itself right there. Okay? And so in that way, so now in calculus, we want to push further than just the average rate of change. And so now we're looking at instantaneous rate of change, the kind of rate that only took place, only happened right at a small instance at 1x value. And that is the whole reason why we're looking at this is the slope of the tangent line. Okay, at x equals a. Okay. So slope of tangent line, or find the equation of tangent line, is not just simply, it's not only some problem, some geometry problem that Mr. Doom brought up throughout the whole quarter so far for you to have work to do. No, it's not simply that. I wanted you to be fluent throughout all those time until now. When you arrive here, you know what the slope of tangent line is for. Because now let me bring in also another side talk right here. So think about the idea like this. So now I just brought in, and we haven't gone too far, okay? We haven't really gone anywhere too far, but so now as you realize there is the existence of instantaneous rate of change. You have a graph. Let's say my graph can be doing things like this. Maybe I didn't draw that bent enough, but think about at this instant, at every instant, you have a different rate of change. That's why, every point we have a different tangent line through it. Okay, and of course, forgive me that my human capability is not precise enough to draw the best tangent line out there. That's why we have to leave that for computers sometimes. But the point now is that think about this graph right here, and let's pretend that this marker of mine is a tangent line. So see at this point. Look at this point that I'm at right now. That's why it's called instantaneous rate of change. Okay, so when x equals a, I have a slope of tangent line being about that much, not too high slope right here. Okay, but think about some instance before x equals a. You got my word, right? There's some instance before x equals a. Maybe some x equals a prime, some instant before that. Then my slope of tangent line was like that. So think about it. See, there are infinitely many instances in between a prime and a right here. So when I moved from a prime to a, my slope of tangent line were changing. See what I'm saying there? And now as I hit to a and decide, think about walking. And so dropping could represent that you going back, kind of heading home from wherever you were. So you're heading home, and at some point you turn your direction and head away again. On one linear path, you're heading home at some speed, and then maybe your speed was slowing down, and then at some instant you're turning around and go the other way again. And that's why we're doing this. But now as far as the rates, how fast your pace, how it is, think about at this instant, when you came to that instant of time and you decide to keep the same rate steady, then your graph is not going to go bend up like that. Your graph is actually going to go like this. And that's why it has been if we're putting this line together with the actual graph, this line here is called the tangent line. Okay, because the idea now is that, see, the graph itself is bent, but pretend that, hey, if you're following along with that graph and right at that instant we decide to keep the same rate, then the graph is actually going to go with this path instead of the other path. But the reason now it actually went the other path because there has been so much change in the rate of change. Okay, and so these are, that's just some introductions about the existence of instantaneous rate of change. And so this is now, so just now I point out the rate of change is the slope of the tangent line at any instance x equals a. And so now it all connects. Slope of tangent line at any instant x equals a is our big responsibility. Find the derivative. That is the derivative at the value a at the instance x equals a. All right, and so now at this point, as anyone following along with the lesson here has come to the realization that the instantaneous rate of change exists out there, because we grew more mature in math, and we actually realized that it's better to have the instantaneous rate of change. So now, summarizing what I have been saying and explaining, then as far as rate of change, we have two kinds. So in the earlier day when we were studying in algebra, then our rate of change were being referred to as, now kind of looking back at what we learned, and we refer to those as the average rate of change. Okay, that's what we did in algebra, and we need an interval. So for average rate of change, yes, we do need a final point in your interval, final y value, subtract the initial y value, and we divide by the difference b minus a. Okay, and that's what a lot of time we had the famous understanding delta y over delta x and all of that. Okay, but in general, anytime we're taking the kind of rate of change that took place over a finite or a definite interval like this, where you knew the starting and the ending of your interval on the x-axis, on the horizontal axis, or on the independence variable axis, then we call that it's the average rate of change. Okay, and so just now we came to the understanding that there is the instantaneous. There's the instantaneous rate of change. And that's what we do, the calculus people do. We want to study the kind of rate of change that happens only at a point. So rate of change, okay, so I have to clarify, at a given value x equals a. And so that's why the way of doing this, we have to take the derivative of the function at that specific given value a. Two different approaches to get that. And so now I have to point out this agreement for the rest of your study in calculus. And for anyone, this is how I'm going to tell you. So starting this point, after you finish, after you've learned about the calculus and learned about how to take derivative, then from now on to the rest of your study and your career studying about mathematics, then and of course any point on after calculus, then anytime we say the word anytime we say the word rate of change, we do refer to the better version, the instantaneous rate of change. So that means, for short, anytime from now on when you hear me saying, or you hear anyone who also study calculus say, find the rate of change, automatically understand that as they refer to the instantaneous rate of change, because that's always the better, the precise version of rate of change. And then anytime you really have to look at average rate of change, then we actually have to be specific. So looking back at those kind of rate of change we've learned back in algebra, then to refer to those kind of rate of changes we learned back then we have to refer to them as the average rate of change. So And that's my point. So from now on, if you just hear the word for short, rate of change, I mean the instantaneous rate of change. But anytime I would like to tell you that, hey, we specifically need to look for average rate of change, I would tell you specifically it's average rate of change. Okay, and so now, at this point, let's look a little further. And I don't want to rush into examples yet, because I want to point out as much detailed explanation as I could in terms of the generality. And then once we've had all this full, complete generality, we're going to drive that into each of the little separate application as example. Okay, and so now, so in my demonstration graphs earlier, and I brought it on a computer screen as well, but we only seeing our graphs going one way. So let me one more time bring the screen back. Okay, so on our computer screen here, you see again, set yourself in the convention that we're reading this graph, we're viewing this graph from the left to the right. So as we are changing our x value from the left to the right, you can see that our graph is, in this case, gaining height, right? I'm using that geometric term right here. We're getting more height as we're going from the left to the right. So that means in this case right here, see, either average rate of change on any interval. Say, let me put back the interval here. Either you're looking at an average rate of change, okay, and looking at the slope of the secant line here, connecting through the initial point and the final point, we're still looking at a line that's rising, because our graph is going up from the left to the right. Our graph is vertically rising. Okay, our graph is vertically rising. But then, now let me hide all of this away. But then what happens when our graph is like this? And as a matter of fact, a lot of time when you're looking into your real-time application problems out there, the graph doesn't only go one way. Any graph a lot of time doesn't go only one way. It's going, there are ups and downs, there are up and downs. Okay? So before we drive into a really good understanding and bring that into the examples later on, I want to emphasize that. So now, either you're looking at instantaneous rate of change, say when x equals a specific value a here. At that instance, when x, your independent variable, equals a, then you have a slope of tangent line, but only at that instance. But right now, looking at that slope, then I can see that we're having a line that's pointing up, and again, going from the left to the right. Then, at least right at that instance, we have a tangent line that's rising up, and the tangent line is still rising up here. So what does that mean? That means at least, and you can see that here in this other instance, I'm using that term now, then my rate of change when at this other instance, x equals b, for example, that I have a different tangent line. And this different tangent line is already having a different slope with the first tangent line that I drew right there. But in the end, these tangent lines are all having positive slopes. Okay? That means that in the end, the y variable is still gaining value, it's still getting more value, it's still increasing in value. And I'm now starting to use that term, but I will get more into using that term later on when we get into that kind of application. But in the end, so the rate of change here, another way of seeing that, the rate of change here is positive, because see, either I put a slope here or I put a slope here of the tangent line. Okay, that slope is, and you already learned that through your algebra, it's anytime the line is from the left to the right is going up like that, the slope is positive slope. Okay, so that means the derivative at b here has to be a positive value, and the same here, the slope of the tangent line, the derivative at x equals a has to be a positive value. And that's as an impact for the graph, it means the graph is still rising from the left to the right. The graph is still rising. Okay, and so what about in these, about your eyes can see it? I believe your eyes can see it. So in an area kind of like in here, okay, then what if I put a tangent line on an instance about there? So now I'm done enough with these points. So let's put it out. This instance here, let's call when x equals some value c right here. And if we place a tangent line right here, then we're going to have our tangent line from the left to the right. Again, it's dropping. And you can see generally that the graph here is losing its height. The y value is losing its height here as we go further. Okay? And so, yes, this is when we have negative or f prime at c, the instantaneous rate of change. The rate of change here is negative. It has to be a negative quantity. I didn't even get into the real calculation. It's just an abstract idea right now, but it's a generality. Anytime that your slope of tangent line is pointing down, that means your rate of change. So here, the rate is negative rate. So that instant here gives me negative rate because your function is dropping from the left to the right. It's losing its own height. Okay? And then see, so there, as I said earlier, your graph will always, a lot of time your graph will have a lot of ups and down and up and downs, right? See, so there's another up area over here where things are gaining back up. Think about a people who are doing, think about a person who is doing business right here. Then see, it's very expected that their profits of the company is rising over time and then rise to a certain peak and start making it way down, drop profits. The government changes and things like that, all kinds of different issues that cause the company profits to fall, right? And then fall to a certain peak, and then it hits back up again. And so that's how it is. And then think about a person who's walking. So if you're walking one way, leaving where you were, okay? As you're walking one way, leaving where you were, then you walk faster, or you walk slowing down, and then you have to stop and turn your way back. That's what it is. You see, so as you keep walking, so if this is time right here, and you keep walking, so you were walking fast, and then you're slowing down, and then there's a turning point, and you're gonna make your way back. And the reason we have a graph being spread out because time goes on. Okay, so as time goes on, that's how we realize the up and down of our distance. If this graph is being applied in a motion situation like that. And so in that way, now let me tackle down right at those instances where things are being the turn point right here, the turning points. So what are those turning points mean in your graphical understanding and also in terms of a rate of change? Okay, and then there will be a problem later I introduce a little bit later in the quarter where we also dive further into that concept as well. But see, in a graph like this, see, we were having positive rate of change, and then see, it makes sense that way that before we can get down and turn to a negative rate of change, then there has to be an instance where our rate of change is exactly 0. So here I have to know that there could be whatever instant that is. So let's say maybe it's an instance x equals d, for example. So right at that instance x equals d, then we have, so here I'm going to label that x equals d. Then our rate of the tangent line has to be 0. Because think about, let's bring up that walking problem is to be the best. I started here, I go fast, and I slow down, okay? But then I decide to stop momentarily and turn my way back and speed up right there. Okay, so that's the idea right there. I was walking up fast, so that's why in a short amount of time my graph rises quickly. And then it's still about the same amount of time here, but it's not as much gain. And then at a certain point, my direction changed. Okay, so that's why consequently it leads to that horizontal tangent. Now I'm starting to use that geometric term right here. The tangent now appears a horizontal, or a slope of the tangent line equals 0. Okay, and I will keep coming back with this concept as we progress through the course right there. And then we must have a point where we completely rest. That's a physicists use that term. We come to a rest for what? Maybe turn direction to head back home. All right, so that's how it happens right there. And so now, so just like that, on this graph, we keep heading home, that's why we're losing distance. We're getting closer to home, but then only closer enough. Maybe home is here all the way here, right? So we didn't get close to home enough, but then we're gonna stop again and make our way walking away again. So, and like I said, I want to leave the actual real complicated problem for the physics instructor when it talks about motions for them to teach any of you, but think about one person but walking on the same linear path and just keep walking back and walking forth. Of course, it doesn't make real good practical sense, but it's a real situation that can happen. Okay, so of course it doesn't make much practical meaning, but it's a situation that exists out there. Okay, so the person can just walk away from where he was and walk back. Okay, and at various different speeds. So speed away and speed walking back. Later on, when I actually get into a real example, I'm also going to bring up a couple of physics terms for that as well. Okay, and so just like that, and think about if this graph is for a person who is doing business, then yes, some days or this is the axis for years, for example. Then in some years, then we got gaining in the profits of the company, and then it's dropping in a certain intervals of years. And then it hits to a bottom where it stops dropping. See, stop dropping, and then start making its way to gain again. Okay, and there are when it comes to looking for applications of rate of change, there's an entire world. There's an entire limitless sky out there to look for applications. It's once you've done with this. The lesson with me right here, start looking for your own application of rate of change out there and anywhere. And from this point on, when you say the word rate of change, it is the derivative of your found function. Okay? And so before I completely close down with all these ideas right here, with all this generality and making our way ready for some actual real example as applications, then I also need to mention another thing that so I was pointing out, when we actually get into the actual examples where we have the function, say, when I'm going to be bringing up some examples about how we make motion, how a particle is moving, and then how a business person is doing gaining profits or whatsoever, or even I'm going to bring up some scientists from some problems for the scientists, that where we have a population of bacteria growth or something like that. But in the end, it is not our job here to know how they come up with those functions yet. Okay, that's the whole reason why you have to take physics. That's the whole reason why you have to take econ courses. That's the whole reason why you have to take chemistry, to understand that how those people come up with how those scientists, those experts, they come up with the function that has those graphs for us to work with. We as the mathematicians, let's say we take, once they already formulated their functions, then we're gonna be able to calculate the rate of change for them. Kind of think about the work like that. So the physics instructor, the physicist, they come up with a function to monitor how your distance changes as time goes on. But with us right here, we found that we learned the derivative, and we solved the problem where how fast things are going at every instance of time, when provided we already had the function given from them. Okay, so that's kind of like the way how it is. So, and at least for us here, the introductory calculus students, then we don't have to worry later on when I bring in the examples. We don't have to worry about how those functions are being brought up. That's for the experts to come up with. Okay, we're just going to be able to calculate the rate of change. We keep things on the simple side for now. And another thing now I need to mention is that, so those functions being given for us so that we can calculate rate of change and all that. So yes, ultimately we come up with those, the experts come up with those to monitor how their quantity changes over another independent variable. But in the end, the formal term for that, we call those functions, those f of x functions. If we apply them into a real life situation, we call them the modeling function. Okay, so it's not only just a graphical problem for doing it for fun. It has real serious applications out there. And when we apply a function, when we developed a function to monitor the changes of our quantity that we work with, we call that it's a modeling function. Okay.